Hi guys. So today there was a Div 3, and if you've done it, you probably know that it was unrated, which is unfortunate. But as I said before, and I made a video on this regarding um, what you can do learning from contests, stuff like that. If you haven't seen it, you should probably check it out. It's somewhat helpful, I would believe. And well, basically, the points it makes is that it shouldn't even matter if a round is unrated. It's going to matter, and this video is probably going to do worse as a result. But it shouldn't matter because everything you can learn from a contest, you can still learn, even if the round is unrated. I mean, you still have a set of problems. You can still figure out your weaknesses and stuff like that. So, there's still some value to be gained from a round, even if it's unrated. But, um, whatever, it doesn't really matter. So, nonetheless, I'm still going to do a solutions video because why not? I have nothing better to do with my time. Yeah, let's see. So this round went pretty well for me. Unfortunately, it's less significant now, but yeah, it was basically a speed contest with everyone finishing within the first 20, 30, 40 minutes, whatever. And so that's what it came down to, basically typing and thinking speed, which I'm pretty good at. So that worked out. And yeah, we have at least 170 people solving full with still 40 minutes left, so I expect this to get a lot better. Oh, wait. Second thread entering the contest late. Nice. See, probably still full solve. That's kind of interesting. Right, okay. And we'll close that. Engineering my thumbnails on the fly. Let's do A. Okay. So this is simple. Let's see if this is going to work. Yep. You have an integer n. You want to see if n has an odd divisor, meaning that there exists some x such that x is odd and n mod x equals 0. The constraints are that n is up to 10 to the 14th and that t is up to 10 to the 4th, meaning that you can't do square root n divisor checking because, for example, 10 to the 4th times square root of 10 to the 14th is 10 to the 4th times 10 to the 7th, which is 10 to the 11th, and that's way too much for even 2 seconds. So that's not going to work, but luckily we only need to check if there exists if there is an odd divisor at all. We don't need to find it, we don't need to find the number, we only need to see if there's an odd divisor. So if we consider the prime factorization of a number, then it can be factorized into something like this. Like, for example, 2 to the a times 3 to the b times 5 to the c times etc., where all these numbers are primes. And notice that the only one that's even is the 2. All of the other primes, all of the other primes are odd. Because if they were even, then they would be divisible by 2 and therefore not prime. So really, we just need to check if any of these primes exist, and if our number n is divisible by any of these primes. And to do that, we need to find the part of n that isn't the 2's that make it up. So we need to get rid of the 2's and then see if it's still prime. And the way we can do that is just get rid of all the 2's. So we do something like while n is divisible by 2, divide it by 2. This is what I do. So read in n, and then while n is divisible by 2, divide it by 2. Then if this resultant number is 1, then that means that n is a power of 2, and so it's impossible. There's no other divisor. And otherwise, if it's greater than 1, then that means that whatever that number is a divisor of n, and it's odd because it's not divisible by 2. So the answer is yes, otherwise. So we just divide m by 2 and remove all of its factors of 2, and then we see if it's greater than 1 or not. Okay, having a bit of trouble with the writing tablet today, not sure why. Let's go for B. So B, I really don't know what they were looking for here. Basically, you're given a number x. You want to see if you can represent it as the sum of some number of 2020s and some number of 2021s. So there should be some value a and some value b, where you take a instances of 2020, b instances of 2021, and all those values sum to x. So we want there to exist these values, and obviously a and b have to be integers, otherwise this would be easy. So like there are millions of ways to do this. You could t is 10 to the fourth, n is 10 to the sixth, meaning that like if you brute force a, then a will go up to it would be between 0 and 10 to the sixth over 2020, which is like small. Let's just calculate that now. So it's like 500, right? And so if you brute force a, then really we want to see if there exists some integer b such that b times 2021 is equal to x minus a times 2020. This whole thing is a constant, so we just need to see if this exists. And therefore we just need to see if this we need to see if this is an integer, meaning we just need to see if this part is divisible by 2021. So that's one way to do it. We can fix the number of 2020s we take. We can also just, what I did myself was like a form of knapsack, where you know that, like for example, it's like a DP, because I found this easier to write. And if you're going to criticize me for overcomplicating this, I wrote this in 1 minute, so that's on you. Basically, you know dp0 is true. Or dpi is, can you make I? We know dp0 is true. Then we know that dp of x also implies that dp of x plus 2020 is true, because we can make this number by making this number and then adding another 2020. And we also know that this implies that x plus 2021 is true. And then this is our transition, and we just go from 0 to whatever, 10 to the sixth. So that's another way to do it. Really, however you want. Some people might have an easier time with fixing the number of 2020s, and that's fine. Personally, I've done this sort of thing a lot, so I just pre-computed DP, and then before even running the test cases, I compute the DP, and then afterwards, it's just checking if you got it or not. Many ways to do it, many ways. See, I may have overcomplicated this, but I'm not sure, so we'll find out. If you have a better approach, you can tell me in the comments, I guess. Basically, you have a list of pairs of numbers. Let's see, 1, 2, 1, 3, 2, 2, and 3, 4. And you want to find the number of ways to pick two of the pairs. So you want to pick a pair of the pairs. And then we're going to line these pairs up. And we want it so both the first and the second elements are different from each other. And we want to find the number of pairs that satisfy this. So, sorry, the number of pairs is 2e5, standard stuff, too big to brute force. So I don't know a good way to do this other than inclusion, exclusion. But basically the idea is, yeah, we're going to use the principle of inclusion and exclusion. So let's consider some pair. Actually, is there an easier way to do this? I don't know, but this works. So we want to find the number of pairs where we have exactly two different elements. So we can, like, for example, if we have a pair if we have a pair AC and a pair BD, then we can like count the number of elements that are different from each other and then like check it like that. And so the possibilities for numbers of different elements are 0, 1, and 2, because either neither of them are different, one of them are, or two of them. So we want to count the number of pairs where we have the value 2, or the number of pairs of pairs. One way to do that is to do all pairs minus like the rest of the possibilities. because we only have three possibilities. We have 0, 1, and 2. And so the sum of these are all the pairs. And so if we take all the pairs and we subtract out the rest of them, then we're left with just this. So the way we can do that is to, well, we need to figure out the number of pairs with 0 and with 1. And the way to do that is, again, principle of inclusion and exclusion. So first, we count the number of pairs where the first values are the same, ignoring the second values completely. They may also be the same, and that's fine, but we'll ignore them for now. So we count the number of pairs where the first values are the same. Let's call this C1 or something. And then we also count the number of pairs where the second values are the same. For example, here, and let's call this C2. And then, now what about the values where both of them are the same? The problem is that we overcount them because when we do this, we'll count, because like we have that A equals B and C equals D in these pairs. So for C1, it'll be included because the first value is equal to the second. And for C2, it'll be included because the second value is equal to the second. So a pair where A equals B and C equals D will be counted twice, both in C1 and in C2. But luckily, we can also find the number of such pairs where A equals B and C equals D. And we can call this C3, for example. So if we consider these numbers, we know that C3 is equal to the number of pairs with 0 differences, where both of them are equal. This is exactly equal to this. And C1 plus C2 is almost equal to the number of pairs where we have exactly 1. But the problem is, like, it overcounts. And yeah, it overcounts in that, like, it counts every pair with both elements equal. It'll count them twice. So to find the number of things where we have at least one, or we have, sorry, at most one that are the same, or at most one that are different, we want the quantity C1 plus C2 minus C3. Because C1 plus C2 gives us all of the pairs with equal 1, and then it gives us the number of pairs with equal 0, but it counts them twice, meaning that we have to subtract this one out to make this count exactly once. And then the final answer is the total number of pairs minus this quantity. So in this case, the answer would be k times k minus 1 over 2 minus this quantity, C1 plus C2 minus C3. And that's the way we can do with an inclusion-exclusion. To count the number of pairs where these are equal, we just stick them all in an array and sort it, or use a map, or however you want. We can do the same thing here, and then doing this is just the same, except we consider equality of pairs instead of just singular numbers. And if you want, you can just compress the pairs into single numbers, and that works anyway. So yeah, basically blindly applying principle of inclusion and exclusion. It's actually very similar to a problem that appeared on our own contest, MBIT, which is my school contest. And it's very similar in that we asked for the number of pairs where I think it was at least one is equal. So it's basically like, I think it's like the exact complement of this problem. But yeah, it's not a unique idea, I would say. Also, that took a long time. Trying to explain inclusion exclusion. Yeah. Actually, if you want to see the code, I can go over that too. It's like fairly just implementation of that idea. You want to count the number of pairs where the first are equal and the second are equal, and you can do that by using a map. For example, if we know that we've encountered like if we know that we've encountered 5 3s in the past, and then we gain another 3, then this 3 will pair with all of the other 3s, so we gain 5 new pairs. And that's the basic idea. And then we get another 3, so we make that 6, and we continue. And then we do the same thing with pairs, and that's it. So yeah, for D, this one's just like annoying, straight up. We have a bunch of applications. That's the idea. Each application has a value and each application has a amount of memory that it takes up and a value. So let's take this sample, for example, I guess. 5 2 3 1 2 1 1 2 4 1. And so this is the weight. And this is the value. And what we want to do is we want to essentially pick some subset. Right. So we want to pick some subset that, like for example, say we take these 3 elements. We want to pick some subset such that the sum of the weights, like the sum of the weights, is greater than or equal to some value m, or m, which is just given in the input. And we want to minimize the sum of the values. Now, the inspiration for the solution is simplifying the problem. Basically, what if every application had the same value? So for example, we had like 1 1 3 1 2 1 4 1, for example. And we want a minimum size of a subset. Then, well, we want to take the largest ones first, because taking a larger one gets us closer to the value m than not, meaning that we'll end up having a smaller subset. And we want smaller subsets because we want to minimize the total value. So if all the weights are the same, the best thing to do is to take the largest value. So what we would do is we would sort the array in reverse like this, and we would just take as many as necessary until we get to m. Now this doesn't exactly work because we have 2 possible values, but we only have 2 possible values. So that makes things nice because we can do something like, say we fix the number of applications with convenience 1 that we're going to use. So what I'm going to do is a little like implementation trick. I'm going to separate the 1s and the 2s. So all applications with values 1 are have the weights of 2, 3, and 4. And all applications with values 2 have the weights of 1 and 5, I believe. Yeah. So then, say we're going to use like 2 of the 1s, meaning we're going to pick the 2 largest ones. So now we have total weight 7, meaning that from the 2s, because that's all we have left, we need to get weight m minus 7. But now we've reduced this to the problem we just did, where we only have 1 possible weight. Because we have some number of 2s, we want to take the smallest number possible, and we want to achieve some specific value. So the best thing to do is to greedily take the largest values. Now could you see, if we solve this for all possible numbers of the 1s that we take, then that gives us a solution. Because the optimal value takes some number of 1s and some number of 2s. So if we iterate through all possible x's and we find the optimal y that corresponds to each x, then we'll just find the answer, because we know x has to exist. So we're fixing the value of x. We're trying all values of x from like 0 to the number of 1s that we have. And then we want to find the minimum y such that it's enough to take the last y elements, or the largest y elements. And so notice that because all the values are positive, when we increase x, or like when we increase x, then the sum we need to attain gets smaller, because every time, like when we take a new element, we subtract that from m for the problem of solving the 2's, meaning that the sum we need to get becomes smaller, meaning that we need fewer and fewer elements from the 2 array. So as we increase x, y is going to decrease. I don't know why I use different colors here, but as we increase x, y is going to decrease, meaning we can use the strategy of 2 pointers to figure out the optimal value of y as we increase x. Or you could start x at the highest point and notice that y will only increase, because as you reduce the value that, or as you increase the value that you need, you're only going to need more and more of the 2's. So either way, it doesn't matter. Just use 2 pointers to figure out what the value of y is for each x. And so yeah, this was kind of a mess the way I did it. What I also did was I was very careful about the cases of using none of the 1's and none of the 2's. I just did that explicitly, meaning that you can consider only taking 1's and only taking 2's and then solve for 2 pointers. So this is what I did, iterating through x in reverse. So I decreased x, meaning that it went down, and then I increased the pointer for y as x decreased, and then figured out what the answer would be for that. In total, this is O of n because, or actually O of n log n because sorting. The problem statement has recently been changed. Okay. Cool. So this problem is, it's something. I don't know what it is, but it's something. Oh my god, 500 people solving F. Wait, so how? Huh, okay. Yeah, that's a lot of people. Second thread just destroys it, Jesus. Alright, I don't know what the point of this problem was either, but since I'm very sure this has appeared before in like some other contest, and this is sort of the same debate as educational rounds with having like Googleable problems, it's just kind of like, I don't think it's a good thing. But that's speculation, so let's just see what the problem is. I'll tell you how to solve it, and you'll see why it's so standard. In fact, yeah, I'm very sure I've seen this exact thing before. Maybe with larger constraints even. Because they have the sum of n, yeah. So basically you have a list of values. You're going to pick k of them. And you want to find the number of you're going to pick k of the values, and you're going to do it so that it maximizes the sum of the values you pick. And basically you want to find the number of such subsets of k values that maximize the sum. So in this case, for example, there are 2 possible subsets. I can take this, which would give us sum 6, or I could take this, which would also give us sum 6. So first things first, obviously the greedy strategy will work because we're just maximizing the value. So we want to consider taking the k largest values, meaning that we're going to do this. But the question is, which of the largest values do we take? So consider the values in their descending order. Because all the 3's are completely within this interval, we have to take all the 3's no matter what. So our choices for taking the 3's are, we have 1 because we're going to take all of them. And similarly for the 2's, our choices of taking the 2's are that we have to take all the 2's. I'm going to stick on some other elements here too, for example. Like say we have negative values for some reason. It doesn't really matter. I'm just doing that for effect. The array values are up to n, but it doesn't matter. Now our choices for 1 are interesting because we have 2 ones, but we only need to take one of them. Meaning that we're interested in the number of ways to pick one of the ones from 2 possible ones. And this is like the definition of n choose k, or the binomial just drew a music note. Binomial coefficient, or 2 choose 1, which is of course 2. So for the value that's sort of like on the edge of the boundary of the elements we take, the number of ways to do it are the number of values in total. Choose the number of the amount that we have to pick, because yeah, that just does it. So yeah, basically that's what it is. And for any other value, whoa, what the hell? Just unscrewed my pen. And so for any other value, we again only have one option. We're going to take none of them. So really there's only one value we're interested in, and it's this value on the boundary. And then the answer for that value is the number of, again, the number of elements in total. Choose the number of elements we have to take. So for example, for this other case, for 2 with 1, 1, 1, 1, we know that we have 4 ones, and we're going to take 2 of them. So the answer would be 4 choose 2. And for the other sample, 1, 2, where we take 1 element, then we're going to take only the first, and we have to take all the 2s, and we have to take none of the 1s. So this element that's interesting to us on the boundary is conveniently going to be the kth element in the reverse sorted list. So for implementation, it's insanely simple. It's just the count of the kth element minus the number of the kth element, minus the number of the kth element of the first k elements. So really what I did was, like, I just used the map because the constraints are small enough that it doesn't matter, and then count the number of each element in total, and then count the number of each element only within the first k elements. And then just like, it's just that, choose that. So if we think of this like, it's the count of AK among the first n elements, and then it's that, choose the count of AK among the first k elements. This is some weird notation, but that's what I'm saying. Among the first n elements, we count the kth element, and then among the first k elements, we count that, and then that gives us the choice. So almost a one-liner, basically. Like this is all it is. Just k largest elements. Yep. Oh, I just saved that. Okay, that's weird. Yeah, I don't know. I really don't know what the point of this was. So F is a bit cooler, but like also I think it's appeared on some use ago before, so I'm not really happy with that either. Why is this scrolling so weird? Okay, so you have 2 binary matrices of size n by n, for example, like this, 1, 1, 0. And you want to convert it to some other matrix, for example, like this. And what you can do is you can pick some row, and you can flip all of its bits to make it like 0, 0, 1. Or you can do the same thing for columns. You can pick some column and flip all of its bits. Well, that sucked. 1, 0, and 1. Right, so we can do that to either of them. And we can do it as many times as we want. Okay. So here's the basic idea. Let's think about the first element. Actually, let's think about the top left element. Actually, let's do better. Let's think about the first row. We can flip this row, or we can not flip the row. But no matter what we do, somehow we need to make this first row equal to this. We need to make this first row on the original matrix equal to the new matrix. So say we don't flip this row. then what we need to do is we need to flip all of these columns individually to make it so this first row is equal to this one. Meaning that for every element that's not equal on the first columns, we have to we have to flip this column, because otherwise there's no way we could ever make this one equal to a 0, and there's no way we can ever make this one equal to a 0. And then we don't flip this column because we need this to be the same. So if we don't flip this row, then we have to sort out these columns by using the elements in the first row. And then once we do that, now we can't flip any more columns, because if we did, then it would affect the first row and it would screw us up. So the only thing we can do now is we can flip some of the remaining rows to make it equal to that. But that's easy. We just need to check if at every point we need to flip the row or not, and if it's even possible to do so. And that's just checking if the rows are equal, or if they were flipped, would they be equal, and is that true for all the rows? Now that assumes we don't flip the top row. But say we do flip the top row. And my claim is that this case doesn't matter. And here's why. Because if we do flip the top row, then basically we can turn our solution from not flipping the top row into the solution for flipping the top row. Because if we flip the top row, then we can also flip our decisions for... We can also say we flip every other row once, and then we do the exact same solution for not flipping the top row. And then if it's exactly the complement of the matrix, then that also gives us an answer, because we can just flip everything again. So basically you can check the case yourself if you want, but flipping the top row is equivalent to not doing it, because everything else will also have to be sort of inverted. That's kind of shaky. This is kind of an intuitive thing, actually. But that would be the way it works. There should be some way to prove that you don't need to do that. If you do flip the top row, then... Yeah, I mean, that's the basic idea, though. If you do flip the top row, you can also, similarly flip everything else in the matrix. And then whatever solution you had for not flipping the top row would also apply to this, where you just don't flip anything. Because, if you have a solution where you do flip the top row, then you can, sort of flip everything else. I think that's the idea. Or rather, if you do flip the top row, then the columns you're going to take are just going to be the exact opposites. For example, you would take all the columns where there's a 0 in the initial matrix. And I think you can just show that the matrix is eventually going to be like the operations you do are going to be sort of the opposites of doing this, but it still gives you the same result or not. I think easiest thing to do is just to not worry about proving it, and just you can check both cases of flipping the top row and not flipping the top row. But once you settle the top row, the entire other matrix is easy to solve, because again, you know that you can't do any more column operations. So the only thing you can do is check if each row is solvable or not, individually. So yeah, basically that's the strategy. Fix the top row and then let everything else resolve itself. Okay, this one is a doozy. Basically, you have some array. Let's see. What's the sample? 793 1463. Right, and you want to make it so for every pair of elements in the array, for example, 7 and 63, either they're equal or one of the elements is divisible by the other. And in fact, we don't need the first case. Like at least one of the elements is divisible by the other. We need that for every pair of the array. And the way we can do that is we can remove some elements. So for example, like if we removed the 3 and the 14, then that would be invalid because 9 is divisible by 63 and 7 is divisible by 6, or the other way around. 63 is divisible by 7 and 9, but 7 and 9 are not divisible by each other, so that's invalid. But if we remove the 7 and the 14, then this works because 63 is divisible by 3 and 9 is divisible by 3. So we want to figure out the minimum number of elements we need to remove to make the array like this. So the first thing we can consider is sorting the initial values. And then this gives us a bit of insight into what our final array is going to look like. Our final array is going to be like this, like some sort of A, B, C, D, E, F, dot, dot, dot. Whoa, I hate that button. I don't know what that button is, but I'm clicking something. All right, and then, so if we let this mean that A divides B, standard notation, meaning that B is divisible by A, then we need it to be true that A divides B, B divides C, C divides D, D divides E, E divides F, etc. And we can see that it's enough to only consider the adjacent elements, because if E divides F and D divides E, then by default, D divides F. This divide symbol is transitive because a divisor of a number is also a divisor of that number. So basically we only need to consider the adjacent elements being divisible. And this is only true if this has to be sorted. Why do I keep clicking this button? My God. I don't know what I'm doing. This is only true if the initial array is sorted. And if any of these are not true, then like C is not divisible by D, meaning that we just broke the condition. So, because D is greater than C, meaning that C can't be divisible by D, D has to be divisible by C. I think I'm screwing this up somehow. I'm messing up the way I'm saying this, but hopefully you get the idea at least. So we need to find the longest array where this is true. And somehow I feel like this problem has shown up before too. I feel like a lot of these are not necessarily copied, but just like they've appeared before somehow. I feel like I've seen this. I don't know where. I think it was like a div2c or something, but I feel like I've seen this. Maybe it was different. I don't know. Guess I'll look for it later. We'll see. So, and yeah, and the F was a Yusuko Silver problem. It was slightly different, but it was like almost the exact same thing. Right. So we need to figure out the longest array that satisfies this property. And it's sort of like we're sort of, it's similar to trying to figure out the longest sequence, like the subsequence of the array that satisfies this property, because we need to remove some elements from the array, meaning that we're going to keep some subsequence of the array in its sorted order. So we're looking for the longest subsequence that satisfies this property. Now let's consider some element x. So either x is the beginning of its subsequence, or it continues on some other subsequence that starts at an earlier element. And so if we continue another subsequence, we need it to be true that x is divisible by w. Meaning that the only possible values of w are ones that are divisors of x. So basically, now we convert this to a dynamic programming problem. If we let dpi be the longest subsequence, ending where the last element is I, That is like, for example, this subsequence, different color. This subsequence would be considered as part of dp of w because it's the longest subsequence ending with the last value being w, ending on a w. Then if we have some element x, and we're considering what we want to do with dpx, the only things we can consider are divisors of x, meaning that we have the transition of dpx is equal to the maximum of dpw plus 1, where w divides x. So the maximum over all divisors of x of dpw plus 1. And then we set that, and if we already have a higher value of dpx, which I don't think is possible, but it might. No, it shouldn't be possible. If we already have a higher value of dpx, then like that, well, we just set dpx equals the maximum of dpx and this, but I don't think it's necessary. But either way, that's the idea. Over all divisors of x, we set dpx to the maximum of dpw. And we do this for every element in the sorted array. It's necessary for it to be sorted because we know that we're treating this subsequence like a sorted subsequence. And so I guess the way to motivate sorting the array is that like just kind of like try different things again and see what works. And if it's sorted, then if it's sorted, then it's nice because you know what has to be divisible by what. If it's sorted, you immediately know that the element on the right has to be divisible by the element on the left, and that sort of just makes it an easier problem. So that's why you would want to think about sorting it. And then it turns out that when you do sort it, you get this nice recurrence. So for example, it's just this. Find all divisors of all numbers. You can do this however you want. I did like n root n or something. It's naive. You have a 5-second time limit. And yeah, 5-second time limit. So basically just do whatever you want. And then for every number, first sort it, then for every number, just set dpx equal to the maximum of itself and this recurrence, all of its divisors. Because this is considering extending the sequence of x by 1. And if you initially set all dpi is equal to 0, then this also immediately considers the case where you start x on its own subsequence, because x should be a divisor of x, meaning that x is a divisor. X is a divisor of x, meaning that you do consider that case, because initially dpx is 0. So that basically gives you everything. I cannot scroll with this thing for the life of me, so I will not try to anymore. Anyway, yeah, so that was this round. I believe a lot of people ended up fully solving. Let's see, how many people was it? A lot of A, B, C, D, E, F. A lot. I guess people either solved F or G, but not both. So yeah, 418 people. Cost you. Nice. But yeah, speed forces, let's go. That basically settles it. I have nothing more to say. These were the solutions. I expect this round to do worse than usual, or this video to do worse than usual, simply because the round is unrated, but what can you do? Hopefully this contest was still useful to at least some of you. It is sort of educational, just at a very basic level. And E will teach you a bit about combinatorics, so they're not that original, but I think there is some value to be had, nonetheless. And wow, you got many more solves than D. Nice. So yeah, that settles it. Goodbye.